Hello, how are we doing today? I hope everyone's doing great. Today we're going to go ahead and start out with discussion about parametric and polar curves, and this is where we're going to really delve into our conic section. So let's go ahead and just start by indicating that. So we're going to have parametric and polar curves, parametric and polar curves. So the interesting thing about this is that normally when we think about a function, a function must pass a vertical line test. And I think we've been, discussing this ever since our algebraic times. And now since we're advancing into our calculus, we say, okay, obviously that makes sense. That makes perfect sense. We've discussed this forever, but this provides an issue for us, and this has limits that exclude curves with self-intersections, or even such curves that are as basic as circles. Because theoretically, if we look at some examples where we have self-intersections or circles, we see here this is a horrible circle, but I'm trying to draw my best to draw a circle. But we see here that this clearly is not a function because it intersects itself twice, and then also we could see something a little bit less uniform, and we could have a curve that looks like this. It looks like this. So it has a little bit of a loop-de-loop, and it continues on. And the interesting part about this is this would have to have a direction. So, well, it doesn't have to have a direction. We could just say it has a direction. So here we would have this, and it would indicate here, and clearly we would see that this is also not a function for many reasons, but more specifically, it doesn't pass the vertical line test because we have the intersection here, here, and here. So we're going to derive formulas required to find slopes and tangent lines and arc lengths of these parametric curves, and these ones are going to be called parametric curves. So parametric curves, and I think that'll really help us investigate because as we can use a lot of important technology, there's going to be a lot of ways that different worldly examples can follow something that follows this pattern, like we have here over in the second graph, or even a circular pattern that we have over here, and finding those instantaneous rates of changes for this area could be very useful for us as well. So so let's go ahead and continue, and let's say we have a particle. Let's say we have a particle that moves along a curve. You can call this curve anything, C, B, 3, could be whatever you want, in the XY plane. So we're just going to limit this to 2 dimensions. And we want the x-axis and the y-axis. We're going to say that these 2 axes are a function of time. So we're going to say these 2 axes are a function of time. So we're going to denote that with x being a function of time and y being a function of time. And t doesn't always have to be time, but I will tell you for most applied situations that I've seen, parametric equations involved, is that this is actually a function of time. So these guys here, are our parametric equations. These are our parametric equations. So they're going to be the parametric equations that describe the motion for the particle C. So that are going to be for that particle. So the variable t in these is the parameter. So we're going to call the variable t the parameter. That's a horrible way to write parameter. Let me rewrite that so it's a little bit neater. So we'll call this the parameter. And so I'll go back to something that I looked at prior. We'll go ahead and draw that original curve here. And I think we had this little loop-de-loop. So I'll do it in blue. So it started like this, and then it went up, and then say that it goes off like this. So this will be our curve C. And on our curve C, we have these points, and this will be x, comma, y. and this is how we can sketch this. So we're going to have to sketch this in terms of a parameter. This might be something that might be difficult for us to describe in any other way, or even for us to draw in any other way, because of the fact this is not a function. So so that's just a brief overview of the definition of a parameter, and how we're going to use it, specifically in terms of time.